Investigation 8, probability and odds, compound events, and experimental probability. We've done different probabilities before, and so this is just a reminder about what a probability is. It's the event as the ratio of favorable outcomes to the number of possible outcomes, or what you want out of the total. So for instance, if we look at the spinner, and it says the probability that the spinner will stop on 1, that's 1 out of 4 possible. And so our fraction then is 1/4, or a ratio is 1/4. And we can often write those as decimals, or percents between 0 and 100%. So that's 25%, 0.25, or 1/4. The complement of that is what we don't want to happen, or the spinner not stopping on 1. And the spinner does not stop on 1 if it stops on 2, 3, or 4. And so that's 3 of them out of the total of 4 that it doesn't stop on, which is 75%, which is 0.75 as a fraction. And so the complement is what we basically don't want to happen. So if we're looking at a deck of cards and we want kings, then there are 4 kings in a deck of 52 cards. So this is always the total in probability. And the top then in probability is what we want. And so the complement of that is going to be what we don't want. So if 4 of them are kings, how many of them are not kings? And so what we don't want is the other 48 cards out of 52. Notice this, if we add them together, we should get 52 out of 52, which is 1. And so the complement of an event, along with the event, always add up to 1. Sometimes you'll hear the word chance, like a chance of rain. What's a chance of rain? And that's referring to probability. So when we talk about the chance of rain is 60%, what we mean is that it's 60 out of 100. And so the complement of the chance of rain is the chance of not raining. And if its chance of rain is 60%, then the chance of not raining is 40%. Another way to express the likelihood of an event is as odds. Now, odds are very different from probability, because odds are what we want over what we don't want. And so there's no total involved in odds. And so it's easy to mistake this for probability. So think about this. If I have a coin and I'm going to flip it, what are the odds of getting a heads? Well, when we talk about heads, there's 1 head, and so that's 1. And what we don't want then is what's left, which is tails. And so the odds are 1 to 1, and we usually write those as 1 to 1 or 1:1. We don't usually write odds as a fraction, but we should always reduce them if we can. So if we had talked about 2 out of 2 or 2 to 2, we would have reduced that to 1 to 1. And so odds, you have to be very careful, because the probability of heads is 1 out of 2, but the odds are 1 to 1. And so you have to be very careful with this. Here's another example of that. If we have a team that won 7 out of 10 games, and so there's 7 games and 10 total games, 7 games they won and 10 total games, then what are the odds of winning? So the odds of winning here are winning is 7 to losing. And so how many games did they lose? Well, if they won 7 and there were a total of 10, then they lost 3. So the odds of winning are 7 to 3. But the probability of winning is 7 out of 10. Okay? So please be very careful that you do not confuse odds and probability. They're 2 different things. And remember, we don't write odds as a fraction, usually. We usually express them as with the 2 or the colon, one or the other. A compound event is composed of 2 or more simple events. So up until now, we haven't done any compound events. We've all done simple events. And simple events is like finding whether the probability of a heads when you flip a coin, or finding the probability of getting a 3 on this spinner here. But now we're going to combine the 2 of them. And when we combine the 2 of them, we have to talk about sample space. And so sample space is all the possible outcomes that there are. And one of the ways to look at sample space is with a tree, or tree diagram. So if we're talking about a tree diagram and we're going to do flipping a coin, when we flip a coin, our 2 options are heads and tails. But we're going to flip the coin, and then after we flip the coin, we're going to spin this spinner. And so when we spin the spinner, it has 4 parts, so we've got 4 possibilities. We could get a heads with a 1, we could get a heads with a 2, a heads with a 3, or a heads with a 4 on the spinner. So we could also get a tails and spin a 1, we get a tails and spin a 2, tails and spin a 3, or tails and spin a 4. And so if you notice, there are 8 possibilities here, because we could get a heads with a 1, or a heads with a 4, or we could get a tails with a 3. So there's all these different possibilities. And we usually write the sample space out then, not in a tree diagram, that's just to help us figure out what it is. We write them out as heads 1, and we usually write them in a set. Heads 2, heads 3, heads 4, and I'm going to continue this on to the next line. Tails 1, tails 2, tails 3, and tails 4. And so there's our sample space. And remember, that's just a list of all possible outcomes from an event. So now, what's the probability of getting a heads and a 4? Well, which ones of these have a heads and a 4? Just 1 out of 8. So 1 out of 8 has heads and a 4. Now, let's look at mathematically how we find that. What's the probability of getting a heads? That's 1 out of 2. What's the probability of getting a 1 on the, a 4 on the spinner? That's 1 out of 4. And if we multiply those together, 1 times 1 is 1, and 2 times 4 is 8. And so we can find this probability by using this multiplication rule of multiplying what we want in the first outcome to what we want in the second outcome. So what's the probability of getting a tails and a 4? We could look at the sample space, or we could do this mathematically. Getting tails, 1/2. Getting a 4 on the spinner, 1/4, which equals 1/8. Or if you look at the sample space, which one of these is tails and 4? There's only one of them, right? So 1 out of 8. Now, we need to talk about independent events, because what we just did, these are independent events, because if I flip the coin, does the spinner make any difference to how I flip the coin? Or if I spin the spinner, does the coin make any difference to how I spin the spinner? It doesn't. And so these are called independent events. Independent events do not affect the outcomes of the other. So let me give you an example of a dependent event. A dependent event would be if you had a deck of cards and you drew one card and you didn't put it back. Because if you were drawing a card out of a deck, and let's say we're looking for kings. If we're looking for kings out of the deck of cards, then there are 4 kings in 52 cards. But if we take one of those out and we don't put it back, we only now have 51. So that is dependent on the first thing, whether we get a king or not on the first choice. We've taken a card out and we're not replacing it. So that is dependent events. So we have to be very careful though when we're doing this multiplication principle that we just did up on the top, that we're only talking about independent events. All right, the last thing today is theoretical and experimental probability. Up here with this coin and this spinner, I did the theoretical probability. Now, what is theoretical probability and how does it differ from experimental probability? If I was experimenting, I would have to actually flip a coin and spin a spinner and find out how many times I got heads and a 4 when I did that. The theoretical probability is the mathematical way that we figure this out. So mathematically, we know that when we flip a coin, half the time we should get heads. But when we actually do the experiment and flip the coins, so if I asked you to flip a coin 100 times, would you have exactly 50 heads and exactly 50 tails? You probably would not. So theoretical probability is the mathematical, and experimental is the experiment. Okay? And when we do enough experiments, we approach the theoretical probability. So if each of you flipped 100 coins, and then we put all those possibilities together, we would be pretty close to half. And if everybody in this school flipped 100 coins, then we would be even closer to half. Okay, so the theoretical probability is what we know it should be mathematically, but the experimental probability is actually doing it. And experimental probability is the number of times that you got what you wanted out of the number of times you did the trial. So here's a baseball coach wants to select a player to be a pinch hitter. He knows that Cruz has 80 hits and 240 at bats. What's the experimental probability of Cruz getting a hit if he's selected to pinch hit? Do we know a theoretical probability for this? We don't. Everyone is different, so we can't get a theoretical probability of how many at-bats you're going to, or how many hits you're going to get at how many at-bats you do. So this is strictly experimental. So how many did he get? He got 80. That's what he wanted, out of a total of 240. And so the probability then needs to be reduced. So I'm going to divide both by 10, and then 8 goes into 8 once and into 24 3 times. So the probability is 1/3. And so every time he was up to bat, every third time he was up to bat approximately, he hit one ball. So is that a very good pinch hitter? Probably not. We would want something to be about half, because if you think about batting averages, they're not usually very much over half. If you hit the ball half the time when you're at the plate, that's actually a pretty good batting average. This concludes Probability Investigation 8.